In this video, we're going to cover section 1.18, radical chain reactions. Rice and Hertzfeld were able to demonstrate that the kinetic behavior of many organic reactions was consistent with the presence of radicals in the reaction mechanism. Now, radicals are chemical species that contain an unpaired electron. As a result, radicals tend to be extremely reactive. The reaction mechanism for radical chain reactions often involve initiation, propagation, and termination steps. Initiation steps involve the formation of radicals from a precursor species. In propagation steps, a radical reacts with another species to produce radical and non-radical products. And the radical products go on to participate in subsequent reactions. These radicals are often referred to as chain carriers. And finally, termination steps. This is when two radicals will recombine to produce a non-radical product. So let's look at an example of a radical chain reaction mechanism. So here we have a question, and we're asked, using the steady state approximation, determine the rate law expression for the formation of methane from the thermal decomposition of ethanol with an overall reaction as shown. Here we have ethanol in the presence of heat undergoes a thermal degradation or decomposition to give us methane and carbon monoxide. Now, the decomposition mechanism proposed by Rice and Hertzfeld is as follows. The initiation step, they began with ethanol, and in that initiation step, ethanol dissociated to give you a methyl radical and a CHO radical. And there's two propagation steps proposed in this mechanism. The first is the methyl radical produced in the initiation step, reacting with a molecule of ethanol or acetaldehyde to give you methane and the CH3CO radical species. A second propagation step is the reaction of that chain carrier, that CH3CO radical, dissociating to give you yet another methyl radical and carbon monoxide. And one of the more prominent, important termination steps in this mechanism is the recombination of two methyl radicals to give you a molecule of ethane. So these are the four main elementary steps in this radical chain reaction mechanism. And although other steps have been observed, they don't appear to be very important to the overall kinetic behavior that is observed for this decomposition reaction. So although the CHO radical does lead to the formation of carbon monoxide and hydrogen gas, it is not important to the kinetic behavior of this reaction compared with the other chain carriers, namely the methyl radical and the CH3CO radical. So let's determine the rate law expression for the formation of methane in this reaction mechanism. So as a first step, we're going to express the overall rate of the reaction in terms of the species involved in the overall reaction. That is, namely, the decomposition of ethanol, the formation of methane, and the formation of carbon monoxide. This question in particular is asking us to solve for the formation of methane. So that's where we start this particular steady state approximation question. So as shown, the rate of formation of methane is going to be equal to the rate constant K2 and depend upon the concentration of ethanol and the methyl radical. So because the methyl radical concentration is found in our overall expression for the rate of methane formation, we're going to need to solve for its rate of change in this particular question. And that gives us equation 2. So the rate of formation of the methyl radical, because the methyl radical appears in each of the 4 steps, we're going to have 4 terms associated with its formation. It's formed in the first step with a rate constant K1 and dependent upon the ethanol concentration. It's consumed in the second step with a rate constant K2 and dependent upon ethanol as well as the methyl radical concentration. It's formed in the third step with a rate constant K3 and depend upon the concentration of the CH3CO radical. And in the termination step, it's consumed with a rate constant K4 and is dependent upon the methyl radical concentration to the square, because 2 methyl radicals recombine to give you ethane. Now, the reason why we include a factor of 2 here is because we're solving for the formation of a single methyl radical. But in this step, 2 methyl radicals are consumed in that elementary reaction step. So not only do we have a square term, CH3 times CH3, but we also include a factor of 2 to represent the fact that 2 molecules of this methyl radical are being consumed in a single elementary step. Now, because we see the appearance of this chain carrier in this expression, it means that we must solve for its formation, and that gives us equation 3. So this CH3CO radical is formed in step 2 with a rate constant K2, dependent upon the ethanol concentration and the methyl radical concentration, and it's consumed in the third step, one of the propagation steps, with a rate constant K3 and dependent upon itself. Now we have our 3 expressions. We can apply the steady state approximation to the radical species, to the chain carriers. These are the reaction intermediates. And so we can set the rate of formation of the methyl radical and the rate of formation of the CH3CO radical to 0 after we apply the steady state approximation. Now, one thing that we commonly observe with radical chain reactions, and when we apply the steady state approximation to these types of reaction mechanisms, is that we often find similarity between the terms for the chain carriers, that is, expressions 2 and 3. And you'll notice that we have identical terms but of opposite sign in these 2 expressions. We have a K2 term in both expressions and a K3 term, but they are of equal and opposite sign. One trick, if you will, for radical chain reactions when we're using the steady state approximation is to sum these 2 expressions. And that's shown on the next slide. So if we add expressions 2 and 3 together, we get simplification to the following expression. And again, that's shown here where these 2 terms are equivalent but of opposite sign. And so we're left with these 2 terms equal to 0. And that's shown here. So now we can easily solve for the methyl radical concentration by bringing this term over to the right-hand side, or vice versa. We're left with a squared term for the concentration of the methyl radical, and we can solve for the methyl radical concentration by taking the square root of both sides. So that leaves us with the following expression for the methyl radical concentration, equation 4. Now, if we substitute equation 4 into 1, this is what we're left with. We have our K2 ethanol concentration out front, and we substituted in for the methyl radical concentration with our new solution. Now it's a matter of taking this expression and reducing it to a simplified form. So we can start by first moving the concentration of ethanol underneath the square root, which is like including a squared term under the square root. So we're left with a square root of K1 ethanol concentration to the cube over 2K4. Now let's take these rate constants out to the front so as to form a composite, an effective rate constant, and we're left with K2 square root K1 over 2K4. And the square root of ethanol to the cube is simply ethanol to the 3/2. And so the overall rate of the reaction, or specifically what we were asked to solve for, the rate of formation of methane, is equal to K effective multiplied by the concentration of ethanol to the 3/2, where K effective is equal to this composite of rate constants. So in summary, it is typical to see non-integer values for radical chain reactions. This is not surprising to have a 3/2 order with respect to an important reactant. Also, you'll see that when we look at the rate constants within this composite, K2, this first propagation step, is quite important. K1, the initiation step, is also very relevant. And we see this inverse relationship with K4, which we would also expect, because the termination step involved the recombination of methyl radicals, which will reduce, in a way, the rate of methane formation because it's going to stop or terminate the reaction. So if you have any questions about radical chain reactions and how we came up with this particular rate law expression, by all means, send me an email. Thank you.